recorded. Anything else from homework stuff? Anybody? No. Okay. All right. Let's see. 532. Oh, there we go. Now I'm even a little more into the double digits. I like it. We're not quite halfway yet. I still got 24 students. Someday, maybe on the day of the final, I'll see everybody again. It'll be so nice. I look at people and say, who the hell are you? Okay. Anything else, guys? Any other questions from homework, from the quiz? Did you look at your quiz yet? I finished grading them. I will, over the weekend, work on updating the grades. So you'll see your grade with 0 homework and you'll see your grade with all the homework turned in, so you can see how much that affects things. As we get closer and closer to the end is nigh. No questions? Okay. All right. All right. So let's get back into where we left off. We are crazy people. Let me show you this again so you don't forget about it. Not Canvas, but this handout here. Weehaw! Oh shit, I went too far. Yeah, partial fractions. So we did an example of this up here. I even did an example. There's the alternate method. We'll do this again today a couple times, so you at least know it's there if you want to. But you can always do equating coefficients. You can always do that. So we're going to get into this slightly freakier stuff. But let me talk about this while this is up here. This is no different than ever, but I say this often. I really want you to get this. So we talked last time about this guy. I don't remember if we've done an example of this guy yet or not. But the point I was trying to make, and please let this make sense. The bottom, let me just tell you, ready? The bottom is linear. The bottom is degree 1 twice. So when you're writing the A, B, C stuff, the top has to be exactly 1 degree below what the bottom is. Do you see how the bottom here is linear? And the top is a 0 power. The top is a number. Is everybody with me? Over here, I still claim the bottom is linear. It's just written twice. So it's kind of just, to be honest, it's more than just a way to remember it. It's actually more than that. I'm not even just making that up. It actually is linear in a very fundamental sense. But now look down here. This is an example where you cannot factor this piece here, right? And that's obviously can happen. In which case, if that's the denominator, the numerator's got to be a first degree. The numerator has to be linear. I told you the numerator has to be 1 degree below what the denominator is. So here, this is a number because the denominator is linear. The top here must be linear, mx plus b kind of thing, because the bottom is 2nd degree. Why did I put a lowercase c up there? You must excuse me. I'm very sorry. Poor little tiny c.
Sir, can we do an example of that one?
Of course. I just wanted to point out that, just to make that connection with what I said last time. Because the more you get that idea, the easier it is to memorize this stuff, which you must do. Okay. So let's do some examples. Did you say sir? What is that? I'm not
sorry.
My students came up to me and they said, sir. The sir routine. That's what Trump does, not me. All right. Melania came over to me and she said, sir.
You are definitely not Trump.
No. Well, that's one of the nicest things everyone ever said to me. All right, let me highlight myself because it's all about me. All right. All right. So let's see. Just gonna make some shit up here. Let's do one. Let's just get back in the groove. Let's do a very, very simple one just to get back into it. Like what, Jeff? Like this. Yeah, let's do one like this. I like it. That's disgusting. All right. Take a second and write what would be on the other side here. And obviously, I'm being nice because normally you'd have to first factor this yourself, right? So you have to know how to factor to do this shit. You have to know how to factor to do math, period. So what's going to go over here?
A over 2x plus 1.
Good. So you put a general number over one factor plus another general number over the other factor. That's where this guy would have come from. That's why the denominator is what it is. It must have come from something over this piece and something over that piece. Please let that make sense. So it's kind of weird. It feels like, why should we be able to do this? This is kind of awesome. This happens so often in mathematics. You take a guess. In this case, it's a little more than a guess. It has to be this. But you guess what the solution looks like, and you put these parameters in the places that mean I don't know what really goes there, but I know it looks like this. And then you can do shit to figure out what those things are. So the shit we do is we multiply by this on both sides. So it cancels here. Let's see, is that plus you? So I hate writing all that out. I never write all this shit out. I'm just doing it right now so you can see what's happening. But what will always happen is this guy will pick up what he doesn't have. And this guy will pick up what he doesn't have. Because what he does have dies. Now this time, let me do that alternate method first, and then we'll do it the other method second. So the alternate method, I'm not even sure if this book goes over this alternate method. What would I let x equal? Does somebody remember what the alternate method? I want to let x equal something. Like, what would I make it equal?
5.
5 is a great number to make. So if x is 5, this side will be 27. Is that cool? Right, if x is 5, 27. That goes away, that dies, and that'll be 11b. So then b is 27/11. What else can I make x? This is a little bit worse, but well, who cares? Same idea, right? Same idea.
-1/2.
-1/2. So if x is -1/2, this is going to be a little bit more gross, but oh well. -5/2 plus 2 is -1/2. Is that right? I think so. So if you plug a -1/2 in, -5/2 plus 4/2 is -1/2. I like it, Jeff, so far. Good job. -1/2 minus 5 is -11/2, I think. So then you get a equals, the 2's cancel, the negatives are canceled, divide by 11, I get 1/11. All right, let me stop for a minute. Now, if you don't like this method, don't ever use this method. I don't care. You could use this other method. What's the other method? So the first step in the other method, ax plus 2bx. Is that cool? Ax plus 2bx minus 5a plus b. Good Lord, Jeff. So what must a plus 2b be? What must a plus 2b be? I'm not going to, sorry, go ahead.
5.
5, exactly. I like it. So a plus 2b must be 5. And then what must negative 5a plus b be?
Positive 2.
Equals 2. I love it. Does everybody see that? And I love the name of this thing. The official name of this thing is equating coefficients. Because that's the only thing that's going to be true. You know, if these two are supposed to be equal, then a plus 2b has to be 5 because that's what's in front of the freaking x. And then what do I do now?
How did you get the ax plus 2bx minus?
Oh, I'm sorry. So here's ax, right? Right?
Yeah.
And then there's 2bx. And then there's minus 5a. And then there's, so I kind of go back and forth and get my like term shit together, but you can do it however you want to.
Oh, okay.
I like it. So that's what this class is where you need to start noticing the flexibility you have in the processes we use. Because before this class, math 90, pre-algebra, elementary algebra, intermediate algebra, you're just learning the freaking how to walk. And now this is sort of like, well, here's another way you can walk, and here's another way you can walk. And, you know, so that's, it's a weird example, but that's really 176. Pre-calculus is where you start to play with math more. And I know some of you guys are like, Jeff, those two words don't go together. All right, how do I solve this?
Can you make the second equation b equals 2 plus 5a?
Sure, I love it. So if I take this equation, I add 5a over. So b equals 5a plus 2. And then I can take this, shove it in there. So that becomes a plus twice b. So is this cool? 10a plus 4. Is that all right? Everybody cool with that? Twice b, and b is this thing. So all I did was I rewrote 1 there, plugging this in there. Good suggestion. I like it. Oh, thank the gods. Sorry. I'm just really happy when things match up. Do you guys see why I'm happy right now? I don't know if you can even see this. I'm running out of room. A equals 1/11, right? Isn't that what we got over here? Yay! You guys with me? And this is why it doesn't matter which way you go. And then, of course, how do we get b? Well, b is 5 times a plus 2. So b is 5/11. Did I say times 2? Plus 2. What did I get for b? This looks like it might be all right. So 22/11 plus 5/11 is 27/11, which is what I got over there. I like it. Now you're going to organize your work better. I don't have much room. But what is the answer then? The answer is this equals 1/11 times 2x plus 1 plus 27/11 times x minus 5. Right, a is 1/11, b is 27/11. I think I told you last time, the alternate method won't always solve it all the way. So we will see a problem where I'll do the alternate method once and then I can't do shit. And then I have to do this way. But at least if I do this once, I'll know a letter. I'll know more information. It will decrease the number of variables I have here. Okay. So I'm going to erase this.
I have a question.
Yes.
So is this different from the 3 variables you were showing yesterday? Or was that kind of setting it up? to get to this? I don't recall.
No. So this little tiny thing here is a system of equations. And it's easier than the one in 11.2 because it's only got two variables, right? Is that what you're talking about?
Oh, so this is 11.3?
I can't remember what section this is.
Okay.
I don't know.
Okay, yeah, it makes sense.
I'm
Thank
sorry.
you.
I know ideas. I have to look them up to see where they are in the book. This is the partial fractions section. I think it's 11.4, maybe? I don't know. All right. So I'm going to erase all this, and then we'll do a freakier problem. All right, so what if we had something like, what do you got, Jeff? All right, yeah, let's not get horribly freaky yet. Well, let's see. Let's stay safe here. Oh, this doesn't work, does it? Damn it. Let's do no. Okay, let's do this. You could do it, Jeff. No, this will work. Yeah, this will work. This will work. Okay. Let's see how funkadelic this comes out to be. All right. Why did I put it there? Why did I put, what am I doing? All right, let me rewrite this here so I can have a little more room. Oh, this is hilarious, Jeff. I'm used to the giant ass ones I have in the classroom. That's too bad, Jeff. You ain't got that shit no more. All right. Now, does this factor right here? Does that factor? Can you guys see that all right? That's a little bit light, isn't it? I'll use a different color. Does this piece factor right here?
No.
No. Damn. All right. So how do I rewrite this? What's going to go over x minus 1?
A.
I like it. And then what goes over x squared plus x minus 3?
Bx plus c.
Because this is truly second degree, so the top must be first degree. And again, we might discover that C is 0 or B is 0. We might discover that we don't need one of these, but the math is going to make it, it's going to say, oh, it's 0. You didn't need that. But I don't know right now. I've got to cover my ass for all the possible things. Okay. All right. So now let's see if I can do this. I'm going to multiply by this, both sides. So this guy loses him, but he picks him up. And this, oh, look how beautiful this is. Loses him, but picks him up. You guys see what I'm saying? That's a much better way to look at this. You don't have to write all that shit out. All right. Now watch this. This is definitely a problem. Can you realize if you only did matching coefficients, you would end up with a 3-variable, 3-equation system of equations, which you should be able to solve, and so can I, but I don't want to. I don't want to. Does somebody see a value to make x equal that would be beautiful? Such a beautiful value.
1.
Yeah, 1 kicks ass. Look what 1 does. 1 kills both of these. Die. So if I make x1, what do I get here?
One.
Yes, 1. And then here I get 1 plus 1 minus 3. is -1. So I get 1 equals negative a, and there, that's 0, right? So I get a is -1. I know a is -1. Yay. Let me stop for a minute. Do you see why I can't do that anymore? Can I do any more? Can I pick another value of x?
No.
Not really. I kind of could if I do quadratic formula and I figure out what makes this guy 0. Do you want to do that? No, no. So this is what I mean by this won't always get me to the answer, but it will make my work easier. Now look what I like to do. Watch what I like to do. I really want, is everybody cool with what's happened so far? Nothing major's happened so far. And I really, do you really understand why I'm allowed to do this? Does anyone have any qualms about me being able to do this? Okay, I'm going to take that for real. Just in case somebody does and they're not saying anything, this equation is supposed to work no matter what x is. Therefore, I can make x whatever I want to and figure out pieces because it's supposed to work for any value of x. All right, that's enough of that. Sorry. You guys, we know that. We get it, Jeff. All right. So look, here's what I like to do. What do I know so far now? I know I'm going to run out of room is what I know. A is -1, right? Let me go ahead and multiply this out. But look what now can't I bring these over here? Whee. Right, so I'll add x squared, I'll add x, and I'll subtract 3. So what must b be? B.
2.
B's got to be 2. Holy shit. Let me skip you for a minute. What must -c be? God, this one came out nice. This is crazy.
-1.
-1. So c is 1. Let's double check. So if c is 1 and b is 2, 1 minus 2 is -1, which is exactly what it's supposed to be. Everybody, are you all with me? Anybody, is anybody with me?
Yeah.
Okay. So, is my Wi-Fi okay? This is so nice. This is nicer than I thought it would be, to be honest. And so what do I get for the answer? I get the answer is -1 over x minus 1. It's especially nice because they didn't get any freaking fractions. It's almost too good to believe. I should have just said, well, yeah, I thought ahead. I knew that no, I didn't have a freaking clue how this thing was going to work. Not equals, Jeff, plus. What was it? Okay. So that is how this breaks up. And if you don't believe me, get like denominators, put them together, and see if it becomes this, right? That's what that means. How you guys feeling out there?
Can you do another one, please?
Yes, we're going to do another one. All right, here we go. Let's see. Oh, yeah. Okay, I got a good one. All right, I'm going to erase all this stuff. I have a problem that we'll see. Uh-oh, somebody doesn't like it. Just left, man. So what if I got this? Let's see. What do you got, Jeff? Let's make that, yeah, okay. So what do you guys think? We've covered what to do when there's a repeated. So this got multiplicity 3, which means there will be 3 dudes over here. Why did the first dude get so big? I don't know. Okay. What goes on the bottom of the first dude?
X minus 1.
Good. And then what goes on the bottom? Second dude?
X minus 1 squared.
Good. And then the third dude, X minus 1 cubed. Yeah. And then what goes on top?
A. Bx plus.
No. Just B and just C. Because again, this is linear, repeated twice. This is linear, repeated 3 times. So the top will be just a constant on all of them. It only is more than just A or B or C if the thing on the bottom is x squared or x cubed, right? So if I had a x cubed minus 4x squared plus 5x plus 6, the top would have to be ax squared plus bx plus c. That's third degree. The top would have to be second degree. But this is not truly third degree. It is 3 first degree. So it's really a first degree thing I'm working with. That's why the top is 0th degree. The top is a number, which is the 0th degree, which is a hilarious phrase. How are you in karate? I'm a 0th degree black belt. Okay, that's not good. And now I do the same thing I always do. I multiply by the bottom. So this guy's going to pick up a couple of these dudes. This guy's going to pick up one of these. And this guy is just going to lose all the ones he had. Poor little dude. Does anyone have a suggestion on what I should do next? And you're all like, yeah, I can tell you what to do, Joe. No, I mean about this problem.
Make x equal to 1.
Yes. Before I do any multiply, I might as well make x equal to 1. Oops. So I get 3 plus 2 plus 1. I get 6 equals 0, 0, C. C is 6. Yay. Well, that's awesome. So I'm going to go ahead. I can subtract 6 from both sides. Is that cool? Because C is 6. So let me just move it over with the known shit, because this is all supposed to be the unknown shit. He's not unknown anymore. Get over there. And now I can multiply this business out. Can is there another value of x I can use? No. Not, well, to be really honest, you could use other values of x and make different ways to do it, but I'm going to stick a little bit to the book until you guys get more familiar with this. The other way is not any prettier, to be honest, so there's no real purpose to it. So here I can multiply this out, and then I get ax squared minus 2ax plus bx plus a, oh, why am I a 1 there? Minus b, sorry, that should be a b. Bam, bam. By the way, I made a mistake, didn't I? I had a 1 here. The reason I so quickly saw it was a mistake is because everything on this side has to have an unknown, has to have the parameter in it. Otherwise, why would it be on that side? Just like that C is 6, get out of here. All right. So what's A got to be?
3.
A's got to be 3, kick ass. What's B minus 2A have to be?
2.
Yeah, B minus 2A is 2. And what's A minus B?
-5.
-5 is. Any questions over how she got those? I think everybody can see that. Just equating coefficients. The stuff in front of the x here has to equal the stuff in front of the x there. for this equality to be true. Why do I not have to do systems of equations? Because I know what A is. Right? So then if I just plug 3 in, B minus 6 is 2, so B is 8. And then if I plug a 3 in here, 3 minus B is -5. So, oh, I already figured out what B is. But just to, I'm like, why am I getting 8 again? Because you already did it, Jeff. So I know A is 3, B is 8, 6 is C. So then I know what the answer is. 3 over x minus 1 plus 8 over x minus 1 squared plus 6 over x minus 1 cubed. And so if you gave this guy 2 more x minus 1s and you gave this guy 1 more x minus 1, then you could combine them all and you would get this. That's what that means. All right, so let me see. Let me give you one to try on your own. All right, here we go. That's so satisfying. Okay, so what are you going to do to them, Jeff? I don't know. Nothing too weird. Why not? Oh, okay. All right. All right. All right, that should be, all right, let's see. I'll give you a little hint. All right, I mean, the bottom, what can you do with it? Factor on x. Okay, so I would do that first if I were you. So go ahead and try to do that. Oh, neat. Okay. Oh, that one works almost too nice. All right. Let's make sure you guys are on the right track here. So just to make sure you're on the right track, you put an X there and you put the irreducible thing here. So the top of this must be scalar. Ooh, that's a new word. It's a number. And then over here it must be linear. This one works out really nice. So then you would multiply by this. So he would pick up this dude. And this guy would pick up an X. Is everybody doing okay so far? There is a value of X you can use before you start equating coefficients. So anybody figure out the value you could give X?
0.
0, because that would kill both of those guys. So if X is 0, you get -2 equals 2A. A is -1. Now, watch what that means. If I put a -1 here, all these would change sign. I'd have to do the opposite to move them over here. I really want you guys to get this. So I just end up adding this to this side. If I put a -1 here in place of A, then it's -x². I have to add x². So I just add this dumb thing to this side. I don't know if you guys see that. If you don't see that, just plug -1 in, distribute, add it over. You'll eventually get to 6x² plus 2x equals bx² plus cx. Now look how that's insane. This is the best equating coefficients you could hope for. You know the whole answer, don't you? Do you? What's b got to be?
6.
B's got to be 6, yeah. And C's got to be
2.
2. Yay! So then I know this equals -1 over x plus 6x plus 2 over the irreducible, over that thing. And again, if you did get LCD, you put these things together, it would become this. That's the whole idea. Just doing that backwards. Okay. Maybe. All right, I'm going to erase this. I'm going to show you an example. We're not going to work it out, but I just want to show you an example and see if you know how to write the A, B stuff. So what if I had 6x minus 1 over, what do you got, Jeff? X plus 5 times x cubed minus x squared minus x plus 1 squared. Did I make that factorable? I did. I didn't mean to. I don't want that to be factorable. Yeah, okay. So make that a minus 1. Sorry, guys. This is not factorable. I feel pretty confident. It's not factorable. All right. So what the hell does that mean? So what am I going to have? So the a over x plus 5 is simple shit. What's in fact, I'm going to have to write this down here. I'm going to need a lot more room. So this would be a over x plus 5. How many more terms do I need? Just one more?
2 more?
2 more because I've got something that's repeated. So I need this guy, and then I need this guy squared. Dude, and then what goes on top of this dude?
Dx squared
Yes.
cx plus d.
And oh, I'm sorry. Don't reuse letters. My bad. See, we got a already. So this would be bx squared plus cx plus d. Right? And then what goes on top of this guy?
Would it be EX squared
Yep.
plus FX plus FG? What's after F?
And I know what it's like. Don't worry. You're not used to using variables like that far out, but yeah. And then that would be remarkably heinous, right? I mean, this is beyond heinous. All right, so we're not going to do it, but I mean, that's an example of an irreducible that's repeated. Repeated means you have to do it from the first degree, the one of them, 2 of them, up to however many it's repeated, and then each of them gets the full. That's a third power. That's got to be squared. That's a third power. That's got to be squared. So it doesn't take much to suddenly have 7 unknowns. That should not happen to you in the homework, so don't freak out yet. Okay, that's enough of that. That should be enough for you to start some of the problems, get a look at them. I want to get into our next topic, unless anybody has a question. So here's what's a little bit weird. This is always, I don't blame the book for this because it's weird to figure out the order to do things in, but we're going to come back to, I don't know how you feel about vectors, but we're not going to do the full vector stuff. All right. We're going to kind of, let's just do it, Jeff. So here's a vector, right? Let me ask you this weird question. How many dimensions does that vector live in? 2. I love it. So here's another vector. How many dimensions does he live in?
4.
4. I love it. So it could be length, width, height, and time. Good old 4th dimension. Wibbly wobbly, timey wimey. All right. It's a special gift from my Doctor Who fans, if there's any. What we're about to do is we're about to make basically sort of maybe multiverse theory, or just, so let me show you a different way to write vectors. I could write this vector like this. I could write it like this. Or I could write it like this. Is that, like if I said we could do that, like I just did? Would you go, why? No. I mean, you just took the fact that I took a party hat, turned it sideways, and put it on either end of the damn thing. So you're probably okay with me doing that weird shit. There's another level above this. These are vectors written like this. It's basically, one of the best ways to look at it is it's like a whole bunch of vectors living in a house together. So, and it of course is called a matrix. So an example of a matrix would be something like that's a matrix. Do you see there's 3 vectors? And you would not be wrong if you actually disagreed on what the 3 vectors are. Can somebody tell me one of the vectors that lives in this matrix?
5, 2, 9.
Yes, 5, 2, 9. Was anybody else thinking 5, -1, 2? You're also right. So you've got row vectors. So like this would be a row vector. And you've got column vectors. So this would be a column vector. So you have rows and you have columns. I like it.
Can you go diagonal too?
No. And I mean, so the very first thing we're going to do is we're going to talk about the algebra of matrices by themselves. So matrices exist by themselves. They do not have to have, how do I say this? So we're going to somehow use matrices to help us with higher and higher level systems of equations. Somehow. So we can represent systems of equations as matrices. And it actually, believe it or not, makes the work we do easier. That is just one use of a matrix. A matrix means something by itself, but I can use the ideas of matrices to help me solve systems of equations. So the very first thing we want to do is talk about the poor things by themselves, right? They deserve a little bit of time. So we've created yet another freaking thing. We just keep creating shit. It's like, stop it, Jeff. So now we got to figure out, how do these things interact? How do they add? How do they subtract? How do they multiply? Oh, shit, right? So let me get your opinion. Don't worry, I'll correct it, but if it's wrong. What do you think should be true about matrix? Let me introduce you to, we use capital letters for this too. I know we use that a lot, but all too bad. So like I can call matrix A is -1, 2, 7, 3. Matrix B is 2, 5, -8, -1. Sure. What do you hope is true if I ask you to do A plus B? How do you hope that will work? And you're all like, I don't even want to say, because you're just going to dash my hopes and say it's this freaky shit. No. What do you hope is true? How would you say you add these two things?
Like adding them in the same direction. So like -1, 2 plus 2, 5. Or like -1, 7 plus 2, 8, -8.
It's even better than that. What's -1 plus 2? What's 2 plus 5? What's 7 plus -8? And what's 3 minus 1? That is exactly how matrix addition works. Are you happy? If I were you, I'd be happy, because it could have been so much worse. Just wait for multiplication. That's where things get pretty key. All right. Are you guys with me? Does everybody see where that came from? Everybody see how that worked? You add the same components. Like, in fact, let's real quick, before we go any further, let's talk about components of a matrix. Oh shit. I should have dressed up like the architect from the Matrix. Well, you see, Neo, there have been several of them. No, it's not right. Shut up. It's no spoon. All right. So here's a general matrix. All right, now wait, before I go any further. There's so much to give you, and I want to figure out what order to do this in. How many rows does this matrix have?
2.
2, crazy. How many columns does this matrix have?
Also 2.
Also 2. So I would call this a 2 by 2 matrix, just like a 2 by 4 piece of wood, right? So 2 by 2. Right. So it's very easy. Well, what would this be? Holy crap and a half, Jeff. Careful now. What dimensions would that have? Sorry?
A 2 by 3.
2 by 3. It's always row by column. So this is 2 rows by 3 columns. I love it. So let's do the I by J. Or let's not do that. Let's do M by N. All right, here we go. You ready? All right. So this will be A11, A12, A13. This will be A21, A22, A23. All right, let's figure out what happens here. How many rows does my matrix have if it's this big?
M number of rows.
M rows. So this one down here, the last thing here in this first column will be AM1. Do you see how that means? First row, first column, second row, first column. This is how we talk about. So if I said second row, first column of this, that's 7. That's how we locate shit in a matrix. This is how we it's like latitude, longitude if you want to go there. So what's going to be at the end of this first row? How many columns are there?
N.
N. So this would be A1N. This would be, why did you make that capital? I don't know. This would be A2N. So what's the very, very last dude here?
AMN.
AMN. Kicking the ass in. I like it. So for this matrix over there, what would A3, no, Jeff, 2, 3, what would A2, 3 be? You almost can't go wrong. What's the best number to guess?
1.
Yeah, it is 1, but probabilistically speaking, that's the probability of a ballistic, all right, I'm sorry. And then what's this? How would you designate? I'm sorry?
A22.
A22, kick-ass. And that's not that hard, right? That kind of makes sense. You're like, okay, math people, I see why you did that. Maybe. Okay. Now I feel like I can continue. So let me take this poor little dude, call him C. And if I had matrix D here, what do you think is true about C plus D? What's your gut tell you?
That there's still going to be a 3 by 3 at the end, because I would make the bottom rows all.
Ah, see, here's the problem though. The bottom row isn't 0. The bottom row is a blank void. It's not even nothingness. It's what would be there if nothing, not even nothing was there. So that's some freaky shit. You can only add matrices or subtract them if they are the exact same dimension. Because otherwise it's like 2 plus 4, 1 plus 1, blank void, plus 6. So, is that all right? I might have over dramatized. I might have overdone that. So this does not exist. DNE does not exist. Or not doable, whatever you want to say. Okay. All right. That's not too bad. So, considering that matrices are sort of like vectors just on the next level, they really are. They're vectors with more information in them. What do you think this means?
Would you multiply all the numbers by 3?
Yeah, so you get 6, 0, 3. You can do it, Jeff. 3, 27, 3. Yeah, exactly. Thank God. So that's scalar, good old scalar multiplication being its easy old self. I like it. All right, all right, all right. Let me make another matrix here. All right, and watch this. What if I ask you to do this? What if I say, what is 2c minus e? You can do it, Jeff. Take a minute and do that. Figure out what 2c minus e. Why can you do that? Because they're both, what are both of their dimensions?
2 by 3.
2 by 3. So you can do it. So go ahead. I'll stand here. Time flies by. So it's not a bad idea to go ahead and rewrite each of these. Now, the way I do this to keep myself straight, so it's like 2c, I'll do 2c. So 2c is easy. Let's see if you can do it, Jeff. I'm not. There you go, buddy. And then I do this plus, and then I just change all the signs of e. Do you understand? Is that cool? Just so I don't make a negative mistake. Negative mistakes are really easy to make in the brain. So I just bring a negative through and I just change all the signs, change sign everywhere, sign. And now you just add them together. It's easy. Now you just add them together. So now you get 5, negative 5, 0, 6, 19, 2. Is that cool? Everybody cool? That's nice. Right? You should be like, oh, Jeff, let's do more of this. All right, let's talk about multiplication. And in order to talk about multiplication, there are so many reasons why we define matrix multiplication the way we do. And it's not straightforward. It's not what you would expect, but it's not that crazy is what I'm hoping you'll agree with me. All right, let me leave that up there for now. So this is the last thing we'll talk about. Not forever, but for tonight. Matrix multiplication. So if I have, let me ask you this. Let's start off with, real quick. Remind me how to do, this is going to be related somehow, but not as directly as you fear. Don't freak out. Please stay with me. How do you do this dot product? You can do it, Jeff. There you go, buddy. Do you remember how nice that dot product was? No, you forgot? Anybody have the answer? What are you guys all right? What does anybody remember? Is it just me and Amber here right now? What happened?
I think I remember, but now I'm questioning everything. Would it be like 4i?
You don't have
No?
to do that.
We're not doing that?
I mean, you can, but there's zero reason to do that. It's just 4 times 2 plus -3 times 1.
Okay.
Right? So here's the I position and the I position, the J position, the J position.
Yeah.
And the ones that are cross, if I was thinking about, what do you call it, Jeff? Foiling shit out, those die because that's I dot J and J dot I and they die, right? Does that sound familiar to you guys? So let me write it. So then you get 5. Let me write these like little matrices. So the way you would write the second vector is you would write it like this. Because we define matrix multiplication to be across dot down. So it would still be 8 minus 3 is 5. And there are several reasons we define it that way. Some of them are not going to be immediately discussable because we have to get a little further. But it basically is the dot product. So what do I do when I get a bigger frickin' matrix, Jeff? And not just a little vector, huh? All right, this is what you do. Remember that a matrix is basically a collection of vectors, right? So if I have, let's see, you can do it, Jeff. Can you do it, Jeff? I think you can. All right, so let's do 1, 3, -1, 0, 5, 2 times, just do something. Here it comes, 2, 5, -1, 6, 3, 0. All right, I like it. Let me ask you this. Could I add these 2 vectors together? Try again. Are they the same size? How big is this guy? What's the dimensions of this dude?
2 by 3.
2 by 3.
2 by 3. What's the dimensions of this dude?
3 by 2.
But I couldn't add them, right? But I can totally multiply them, and I want to make it really make a lot of sense as to what you can look at to see if you can multiply things. Do you see, since I'm doing across dot down, the number of columns has to match the number of rows, which really just means this number has to be the same as that number. Do you see that? This number has to be the same as that number in order for me to be able to multiply these. Right, so this inner stuff. And the really, does everybody see that? If I had one more column, this would go to shit because then there wouldn't be something for that last number to go with. So if 4 and 3 can't do it. The really, really cool thing is, how big will the answer be? The answer will be a 2 by 2. So the inner has to match, and the answer will be this by this. So let's see why that makes sense. Because how many vectors do I really have? I have 1, 2, 3, 4. So it makes sense that my answer is going to have 4 entries. So what do I get when I do this dot product? I mean, that vector dotted with that vector. I get 2 plus 15 plus 1. Can you guys see that? It's exactly like a vector and a vector. I just write it like this and like this. And one really basic reason we do this, and this is not the real reason, is it's easier to track if one of them's this way and one of them's that way. 2 plus 15 is 17, plus 1 is 18. So I'll put an 18 right there. In fact, where does the answer go? Well, this is the first row, first column. So the answer goes in the first row, first column. And then I do this and this. First row, second column, so that's going to be the answer that goes here. 6 plus 9 is 15 plus nothing. And then remarkably enough, I'll do the second vector down here times the first column. So now it's going to be second row, first column. Second row, first column is going to be the answer that goes here. 0, 25 minus 2 is 23. And then I do the second row, second column. That's second row, second column. The answer goes here. 0, 15, 0. Okay, that's neat. I like that. Cool. So let me show you this. Riley. I have put up on the website. I have put something that I hope will help. So again, there's the partial fractions, and then in the same spot, there's matrix multiplication. And I have a couple of examples. And here's something very interesting that it's, I could have done up there, but too bad I didn't. In fact, well, watch this. So here I give two matrices, and then I multiply A times B, and I get that answer. And then I multiply B times A, and I get that answer. Are they the same? So we have created these brand new objects, these mathematical objects we call matrices, where multiplication is not commutative. Do you remember the commutative property of addition and multiplication? Meaning like 2 times 7 is the same thing as 7 times 2. It works for numbers. It does not work for matrices. They're not commutative. In fact, look at the second dude. How big is A here? What's his dimensions?
2 by 3.
2 by 3, and this guy is only
2 by 2.
So could I multiply them A times B?
No.
No, because this is 2 by 3, and this is 2 by 2. So the 3 and the 2 don't match. The inner stuff don't match. So I couldn't even do AB. It cannot be done. But if I do B times A, that will work. So if I write the B first and the A second, I can see that this goes perfectly with that, right? I mean, the inner ones match then. 2 by 2, 2 by 3, the inner ones match. So that's an even more extreme example of why they're not commutative. If you turn them around, it might not even be able to be done, period. It's always better if I remember all my words. Maybe. So you can have this obviously sitting next to you as you hit these problems in section. There we go. Look at me. Look at past Jeff. Section 10.4. No, it's not 10.4. That's terrible, Jeff. Is this 11.4? Is that what this is? I can't remember now.
I think it's 11.5.
11.5? Well, shit. I think that was the old. That's why I was surprised. I'm like, I don't remember doing that. That's the old pre-calculus book I used to use that cost $170. Sorry about that, guys. So it is section 11.5. Okay. So you got that handout up there to help you out with the matrix multiplication. The addition, subtraction, scalar multiplication, that should be easy. It's the matrix multiplication that needs some getting used to. And you get a little cross-eyed when you do it. I've been there, trust me. Like, oh, we're flip by mine. Okay, I think otherwise I'm good. I'm done for tonight. So let me know if you need to hang out for a bit. Otherwise, you're free to go. Whoo.
Thank you.
Anytime. Have a good
Yeah,
weekend.
thank you.
You too.
Sure.
Oh yeah, I had a question
Yes.
about, I mean, this is pretty simple, but on the quiz, there was a question and it was like sec theta equals 4,
Yes.
right? And I don't know, I ended up solving it, but I feel like I did it in absolutely the wrong way. I don't know, the way I did it, let me check, but do I have it here?
All right, let me see here. Here you are. Okay. Yeah, you got it right. Let's see what happened. Oh yeah, I kind of like the way you did it.
I drew out a triangle and then basically just thought of rise over run, which I could tell was not the correct way to do that.
No, here's the funny thing. Here's something I haven't said. I think I might have said it. Tangent is related to slope. I think I said that at least once.
Yeah. Mm-hmm.
So that's beautiful. The slope of that triangle, the slope of that line there on the triangle is square root of 3 over 1, which is, there you go. And it goes through the origin, you know, in the unit circle.
And what is the proper way of solving that problem?
The proper way to solve it is, what was it again? It was secant theta equals
2.
2. So that means cosine theta equals 1/2.
Yeah, that's what I got. But then
What's missing in front of cosine for it to become a rectangular coordinate?
R.
What is x? Yeah, r is missing. So just multiply both sides by r.
Okay,
So then you-
I guess that makes sense. Yeah, so it'd be 1/2 of r equals x, right? Is that what you would get?
Yeah, and r is the square root of x squared plus y squared.
Yeah.
Because r squared is x squared plus y squared, right? So then you can square both sides, get your like terms together, and eventually you get to what you wrote.
Okay, got it.
The one thing you're missing is it should be plus or minus. But I mean, it's not that big of a deal.
Well, I mean, wouldn't it work either way?
Yes, that's why you have to put both.
Well, no, what I'm saying is like, I don't know, because I was thinking if you had it that way, right? If it was secant of theta. I don't know, maybe I'm thinking of it wrong. Would it have to be plus minus?
So think about it. When would the cosine be 1/2? Couldn't it be in the first quadrant or the fourth quadrant? Right?
Yeah, that's true.
Which
Okay.
means the slope could be positive or negative, because then it would be going down in the fourth quadrant, right?
Okay.
So your process is correct. You'd have to kind of remember that to see that as plus or minus, or if you did it the way we just discussed a second ago, when you take a square root, you put plus or minus.
Yeah. Okay.
You know, either way. But I liked your approach. That's why I didn't take any points off. I don't mind about that. That was a good idea.
All right. Well, thank you.
Sure.
Okay. See you.
All right.
That's it for me.
Take care, man.
Yeah. Have a good weekend.
You too.
Or oh, wait, do we have? Sorry, I keep pulling you, but what are we for Thanksgiving? Do we have any days off?
Yeah, Wednesday. So we're just going to meet Monday, Tuesday. So if you pay attention on the homework sheet, I pretty much indicate that we get Wednesday off.
All right. Sorry about that.
Because I
Okay.
figure, I don't know if anybody actually can travel, but if somebody is going to travel, it's probably going to happen on Wednesday. So I just give us that day off.
Might as well.
Yep.
Okay. Well, yeah. Have a good weekend. See you.
Too, man.